Have you ever heard of a cursed metal hidden inside your smartphone? It might sound like a fairy tale, but the story of tantalum, an element in the periodic table, has all the drama of myth and history combined. Most people have never heard of tantalum, yet it is crucial to many gadgets and technologies we use every day. From phones and laptops to medical implants and jet engines, tantalum's unique properties make it invaluable in modern life. But tantalum carries a darker legacy too. At the turn of the 20th century, this rare metal became the key factor in the Second Congo War, a brutal conflict that claimed millions of lives. Welcome to Cube Chemistry, where we'll discuss all the elements of the periodic system and also do experiments. So if you like these videos and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be doing another experimental deep dive into an element again. Now what we have here is something really special. We got tantalum inside a cube as well as outside of the cube. And if we feel the metal in our hands, it feels extremely heavy and dense. Also, it is very shiny. Now I have a weakness for shiny things, so I immediately think to myself, can you lick it? Yes, you can safely lick pure tantalum, which is also mentioned in the periodic licking table. Tantalum is a highly inert non-toxic metal that doesn't react with saliva or body fluids, which is why it's even used in surgical implants and dental applications. Now, it doesn't corrode or release harmful ions in the mouth, making brief contact like licking generally harmless. I'm not going to do it, so that being said, regularly putting metal objects in your mouth isn't advisable for hygiene reasons, regardless of their chemical safety. Now, to understand why tantalum is nicknamed the cursed metal, we must begin with an ancient myth. Tantalum gets its name from Tantalus, a figure in Greek mythology. According to the legend, King Tantalus was condemned to an eternal punishment in the afterlife. He was made to stand in a pool of water beneath a fruit tree. Now, whenever he bent down to drink, the water receded out of reach. When he reached up for the fruit, the branches lifted the tantalizing fruit away from him. He was forever thirsty and hungry, tormented by offerings just out of reach. It's from Tantalus' name that we get the word tantalize. His punishment was a curse of eternal temptation without satisfaction. When the element tantalum was discovered, the scientist who identified it saw a parallel with this myth. In 1802, a Swedish chemist named Anders Gustav Eckeberg found a new metal in some mineral ores. Now, this metal proved exceptionally difficult to dissolve in acid. No matter what he tried, the substance resisted drinking the acid, just like Tantalus could not drink the water in his punishment. Frustrated yet amused by this behavior, Eckeberg decided to name the element tantalum, after the tormented Tantalus. Now, in Eckeberg's words, the metal showed an incapacity when immersed in acid to absorb any and be saturated, reminding him of Tantalus' ability to quench his thirst. In other words, tantalum's oxide refused to yield to acids, a tantalizing problem for early chemists. This origin of the name gives tantalum a somewhat cursed reputation. It's as if the metal itself was under a spell, stubbornly resisting attempts to be studied. The nickname, the cursed metal, also placed on Tantalus' story. He was a cursed figure, and so tantalum carries the legacy of that curse in its name. Now, tantalum's tale begins in the early 19th century. Anders Gustav Eckeberg discovered tantalum in 1802 while examining two mineral samples, one from Sweden and one from Finland. He suspected these dark, heavy minerals contained a new element. Little did he know that he stumbled upon something that would confuse the scientific community for years to come. Now, just 1 year before Eckeberg's find, in 1801, an English chemist named Charles Hatchett had announced the discovery of a different new element from a mineral obtained in Connecticut in the United States. Hatchett called that element columbium, which we now know is niobium. The minerals containing columbium and niobium and tantalum were very similar. In fact, they often occur together in nature. By 1809, an English chemist, William Hyde Wollaston, took a closer look at Eckeberg's tantalum and Hatchett's columbium. Now, Wollaston compared their oxides and found they had different densities, suggesting they might be different substances. However, the difference was subtle, and he incorrectly concluded that columbium and tantalum were actually the same element. He chose to stick with the name tantalum for both, assuming Hatchett columbium wasn't a separate entity. Now, this was a scientific mix-up that would take decades to untangle. For many years, chemists thought there was only one metal, tantalum in these ores. The situation got more confusing when some chemists claimed to find yet another element in the mix, which the German chemist Heinrich Rose in 1846 named Pelopium, after Pelops, a son of Tantalus in mythology. Rose also proposed renaming columbium to niobium after Niobe, Tantalus' daughter, keeping with the family theme. The result was a mythological charged tangle of names: tantalum, niobium, and supposed pelopium, all lurking in the same kinds of minerals. Now, it turned out that pelopium wasn't a new element at all, but a case of a mistaken identity caused by the subtle chemistry of tantalum and niobium. Eventually, as analytical techniques improved, chemists proved that only two distinct elements were present: tantalum and niobium. The earlier name columbium fell out of use, and niobium became the accepted name for element 41, complementing tantalum. The curse of confusion was finally lifted by the mid-19th century through the work of researchers like Rose and later scientists who conclusively showed differences. By 1866, chemists such as Jean-Charles de Marignac had definitively confirmed that tantalum and niobium were separate elements and not a mix of more exotic species. Marignac also developed a method to separate them, which we'll touch on later. Once chemists knew what tantalum actually was, the next challenge was obtaining the pure metal. Early on, only impure forms of tantalum could be isolated from its ores. And it wasn't until 1903 that a reasonably pure, ductile tantalum metal was produced by a German scientist named Werner von Bolten. Von Bolten's method involved chemically reducing tantalum compounds to get the metal. With this breakthrough, tantalum could be shaped and studied as a true metal. One of tantalum's first real applications came around this time. It was used for light bulb filaments. In the early 1900s, incandescent light bulbs typically used carbonized cotton threads as filaments, and then metals like osmium. Tantalum filaments turned out to be much more efficient and longer lasting than those earlier filaments. The Siemens and Halske company in Germany began manufacturing tantalum filament bulbs commercially. For a few years, tantalum filaments lit up homes in Europe and America, representing a cutting-edge use for this new metal. However, tantalum's time in the spotlight was short-lived. In 1908, tungsten filaments were introduced and quickly proved superior. Tungsten has an even higher melting point and could glow brighter without burning out. By the 1910s, tungsten filaments replaced tantalum in virtually all light bulbs. Still, tantalum light bulb era demonstrated that this cursed metal had valuable properties and could be industrially important. Through the early 20th century, tantalum slowly found more uses as people learned how to work with it. The United States started large-scale industrial production of tantalum around the 1920s. By the 1940s, tantalum was being used in surgical equipment and medical implants, taking advantage of its resistance to corrosion and its friendly behavior inside the body. But the biggest turning point for tantalum's importance came in the mid-20th century with the rise of electronics. In the 1950s, researchers discovered that tantalum could be used to make excellent capacitors, electrical components that store charge. Now, by the 1960s and beyond, as transistors and microelectronics boomed, tantalum capacitors became essential for shrinking circuits down. We'll talk more about those applications soon, but it's worth noting how far tantalum had come from a curious, almost undetectable element entangled with niobium to a metal lighting early light bulbs and finally to a critical high-tech material. Tantalum sits on the periodic table with symbol Ta and atomic number 73. It is classified as a transition metal and is part of the group elements known as the refractory metals, meaning they have extraordinary high melting points and are very robust. Let's break down some of tantalum's most notable properties in plain language. Hard, heavy, and ductile. Tantalum is a hard metal. It can resist scratching and wear, yet it is also very ductile, which means that it can be bent, stretched, and shaped out without breaking, especially when it's pure and refined properly. In terms of weight, tantalum is extremely dense. A cubic centimeter of tantalum, about the size of a small sugar cube, weighs about 16.6 grams. For comparison, that's nearly twice as heavy as a cube of steel, or about 1.5 times as heavy as the same size piece of lead. It's not the absolute heaviest metal, but it's up there among the densest elements we commonly use. This density contributes to its image as a solid, substantial material. Visually, pure tantalum is hard, lustrous metal with a distinctive grayish-blue steel color, as we saw earlier. One of tantalum's star qualities is that it doesn't melt until extremely high temperatures. The metal melts about 3017 degrees Celsius or 5463 degrees Fahrenheit. And that is hotter than nearly any other metal, except for a few like tungsten and rhenium, which we have discussed last week. And if you try to boil tantalum, you'd have to heat it up to around 5458 degrees Celsius, a temperature that hardly any environment on Earth could reach outside of specialized furnaces or perhaps inside of a star. Now, this is why tantalum and its close neighbors are called refractory metals. They literally refuse to melt under normal conditions. Such a high melting point means tantalum can survive in very hot environments without losing its solid strength, which is great for certain high temperature applications. If one property defines tantalum, it's its remarkable resistance to corrosion. Tantalum is often compared to noble metals like platinum in this regard. At normal temperatures, acids don't bother tantalum at all. Now, you can put tantalum in aggressive acids like hydrochloric acid, sulfuric acid, even the notorious aqua regia, a mixture of acids that can dissolve gold, and tantalum will remain virtually unchanged. This metal simply does not rust or corrode easily. Why? Because tantalum immediately forms a thin protective layer of oxide on its surface, tantalum pentoxide. This oxide layer is very adherent and stops further attack, acting like an invisible shield. In the earlier anecdote, Eckeberg struggled to dissolve tantalum oxide in acid. That's because once oxidized, tantalum is incredibly chemically stubborn. Only very particular chemicals can attack it. For instance, the one common acid that can dissolve tantalum is hydrofluoric acid, an acid mixture containing fluoride ions. Hot concentrated sulfuric acid can also slowly get to it, as can strong alkaline solutions at higher temperatures. But in everyday conditions and common acids, tantalum is essentially immune. This inertness is a huge advantage for applications where we need a material that won't degrade or react. Tantalum is a metal, so yes, it conducts electricity and heat well. Though not as spectacular as copper or silver, its electrical conductivity is decent, which is why it can be used in electrical components. Its thermal conductivity, ability to conduct heat, is moderate among metals, but combined with its ability to withstand heat, it becomes useful in heat-sensitive and electrical context. We mentioned earlier how tantalum's discovery was muddled with niobium. Chemically, tantalum behaves a lot like niobium, which sits just above in the periodic table, element 41. In technical terms, both usually have an oxidation state of +5, form similar types of compounds. The reason for their likeness is partially due to something called the lanthanide contraction, a subtle effect in the periodic table that makes atoms of heavier elements like tantalum a bit smaller than you'd otherwise expect. As a result, tantalum and niobium atoms are nearly the same size and their ions fit into similar structures, making their chemistry hard to tell apart. For a layperson, a key point is that these two elements are like siblings with nearly twin personality, which is why early chemists had such trouble distinguishing them. Even today, separating tantalum from niobium is a tricky process because whatever chemical trick you try, both elements respond in almost the same way. Every element has different forms of atoms called isotopes. Natural tantalum is interesting in this regard. Almost all of it is one stable isotope, tantalum 181. But tantalum also has a tiny fraction, less than 0.1% of another form, tantalum 180M, which is actually a metastable isotope. Now, metastable means this isotope is in an excited energy state, and in theory, it should eventually release that energy, K, to become something else. But tantalum 180M has never been observed to decay. It's like an excited atom stuck in limbo, possibly for billions of years. It's exceedingly rare, the rarest stable isotope in nature, and it's a scientific curiosity more than anything practical. Now, we won't dwell on it for too long, but it's a neat trivia. Tantalum has an almost undying isotope, which feels oddly appropriate given its mythological namesake suffered an unending fate. Tantalum has no known essential role in biology. Our body doesn't need it, and you won't find it naturally in your bloodstream or anything like that. However, tantalum is biocompatible, meaning that if it's placed inside of the body, say a medical implant, it doesn't react or cause rejection. The human body basically ignores tantalum instead of treating it like a toxic intruder. This inertness in tissues is another important property that we will see used in medicine. Now, these qualities, like chemical inertness, made it very challenging to isolate it in the first place. Next, we will explore how and where we obtain tantalum, given that it's such a rare and obstinate element to extract. Despite tantalum's valuable properties, Mother Nature didn't make it abundant. It's a rare element in the Earth's crust, estimated to average only around 1 to 2 parts per million. This scarcity is on par with elements like uranium. It means pure tantalum metal is not something you stumble upon easily. You have to mine and refine tons of rock to get a small yield. Tantalum isn't found in large pure chunks in the ground. Very, very rarely, a tiny bit of native tantalum metal might be found alloyed with other metal, but that's extremely uncommon. Instead, it's typically locked inside minerals. The most important tantalum-containing minerals are columbite, tantalite, and its variety. If that name sounds a little bit clunky, there's an industry nickname for the mixture, coltan. Columbite is rich in columbium, the old name for niobium. Tantalite is rich in tantalum. In nature, you usually get the both together, and the ratio can vary. These minerals often occur in granite pegmatites, which are basically very coarse grained veins that form as the last bits of molten rock cool down, often carrying rare elements. Now, for those not into geology, pegmatites are the odd pockets in the Earth's crust where gemstones and unusual minerals form. Tantalum likes to hide out there alongside niobium, tungsten, and even tin. Interestingly, a lot of tantalum is also obtained as a byproduct of tin mining. Certain regions that mine tin, for example in parts of Southeast Asia or Africa, found that their tin or cassiterite deposits also contain tantalum and niobium in leftover material. When they process the tin and smelt it, the waste slag can be further treated to extract tantalum. In the case of turning trash into treasure, recovering a valuable metal from what would otherwise be discarded. Tantalum mining is geographically concentrated in only a few areas. Historically, significant tantalum production came from Australia, Brazil, and certain African countries. Around the late 20th century, Australia was the leading source. It has large deposits like the Greenbushes and the Wodgina mines. However, mining operations can wax and wane with economics. Australia's mines have at times paused production when prices were low or due to market shifts like a big dump of supply from elsewhere. Brazil is another major source. It has substantial tantalum reserves and currently remains one of the top producers. In Africa, the picture is complex. Countries like Rwanda, the Democratic Republic of Congo, Nigeria, and Mozambique have produced significant tantalite and coltan. In fact, in the 2010s, Rwanda became one of the world's leading exporters of tantalum concentrates. Now, this is a remarkable shift given that a decade or two earlier, the Democratic Republic of Congo, with its rich deposits in the eastern regions, was infamous for tantalum production. We must touch on an unfortunate chapter of tantalum's history, its status as a conflict mineral. In the late 1990s and the early 2000s, global demand for tantalum spiked, partly due to the rapid growth of the electronics industry. Think the cell phone boom. This made coltan ores highly valuable. In the Democratic Republic of Congo, which has large coltan resources, various armed groups took control of the mines or trading routes, using the profits to fund a brutal war. The term blood tantalum or conflict tantalum emerged much like blood diamonds because this valuable material was contributing to conflict and suffering. The metal that got its name from a cursed myth seemed to be cursed in reality too, bringing misery in its sourcing. International awareness led to efforts to curb the trade of conflict minerals. Laws like the U.S. Dodd-Frank Act 2010 now require manufacturers to disclose if their tantalum and certain other minerals might be from conflict sources, pressuring companies to source responsibly. Now, the situation has improved somewhat. Rwanda's rise in tantalum output, for example, is part attributed to more regulated mining, though Congolese ore likely gets mixed in. It's an ongoing challenge to ensure tantalum supply is ethical. So tantalum is rare and often tied up with niobium in the ground. That leads to the next big question. How do we extract and purify tantalum? The process is quite demanding, one of the more complex separations in metallurgy. Here's a simplified overview of how tantalum is produced from its ore. Ore containing tantalum, coltan, or tantalite is mined from the earth. These ores are usually heavy and can be enriched by simple means first. Miners often crush the rock and use gravity separation because tantalum minerals are much denser than the surrounding rock. Imagine swirling crushed ore in water or shaking it on a table. Heavier minerals will settle or separate out. This yields a concentrate that has a higher percentage of tantalum and niobium than the raw ore. Now, the concentrated ore, which still contains both tantalum and niobium, plus other impurities like iron, manganese, and titanium, etc., is then treated with strong acids, typically a mixture of hydrofluoric acid, HF, and other acids like sulfuric is used. Now, why hydrofluoric acid? Because neither tantalum nor niobium oxides will dissolve in most acids, but they will form soluble fluoride complexes in hydrofluoric acid. In this leaching process, the ore is digested in acid, and tantalum and niobium get into solution as fluoride compounds. For example, one compound formed is something like H2TAF7, a tantalum fluoride complex. Now comes the tricky part, separating the two twin elements. One modern method is solvent extraction. The acid solution containing both metals is mixed with an organic solvent that has an appetite for one of them more than the other. By carefully choosing conditions, processors can make tantalum prefer the organic phase while niobium stays in the water phase, or vice versa. Older methods involve fractional crystallization, slowly cooling the solution or adding potassium fluoride to form solid crystals of potassium tantalum fluoride, which is less soluble than analogous niobium salt. Essentially, chemists exploit slight differences in solubility or chemical behavior to pull the two elements apart. This can require multiple steps of extraction or crystallization to get high purity separation. It's a bit like an elaborate dance to tease apart two nearly identical twins. Now, after separation, tantalum is typically converted into a solid tantalum oxide or a complex salt like potassium tantalum fluoride. For instance, in one route, the purified tantalum solution is neutralized with ammonia, causing tantalum to precipitate as an oxide or hydrous oxide, which is then calcined, heated, to get tantalum oxide powder. Tantalum oxide or fluoride salt then needs to be reduced to metallic tantalum. One common method is a chemical reduction using a reactive metal like sodium or magnesium. For example, potassium tantalum fluoride can be heated with sodium metal. Sodium eagerly bonds with the fluorine, freeing pure tantalum in the process. Now, this is somewhat analogous to how reactive metals are used to produce other difficult metals, like how sodium was once used to produce titanium in the early Kroll process, and we should still discuss the Kroll process in one of our videos. The reaction yields tantalum metal, usually as a fine powder, and sodium fluoride salts as a byproduct. Another approach is metallothermic reduction of tantalum oxide using carbon or aluminum, but those can introduce impurities, so sodium reduction is preferred for high purity. Now, sometimes the tantalum powder is consolidated by pressing and sintering, heating without fully melting, to make a solid piece. For very high purity and dense metal, tantalum can be melted in a vacuum or an electron beam furnace. There are also modern methods under development or recently introduced. One notable method developed in the late 1990s is a molten salt electrolysis process, somewhat like how aluminum is made, but modified for tantalum. In this process, tantalum oxide powder is directly reduced to metal by passing an electric current through a molten salt bath in which the oxide is dissolved. Tantalum collects at the cathode as a metal. This method could simplify some steps and was reported to produce a few percent of global tantalum at the pilot scale. It's an active area of research for making refractory metals more efficiently. Now, throughout all these steps, the main theme is that extracting tantalum is hard work. The presence of niobium is a constant headache because of their chemistry similarities, and the need for harsh chemicals like hydrofluoric acids and multiple steps make it one of the more expensive metals to produce. The supply chain can be volatile, mines ramp up or down, and global events can affect availability. Tantalum is considered a critical raw material by many governments, meaning it's both economically important and at some risk of supply disruption. Recycling has become very important. Scrap tantalum, like old electronic components or waste from capacitor manufacturing, is collected and refined to retrieve the metal. In recent years, recycling has supplied a significant portion, sometimes a third or more, of tantalum used in industry, which helps alleviate the pressure on mining. To put things into perspective, the world only produces on the order of a few thousand tons of tantalum per year. This is tiny compared to common metals. For example, iron production is hundreds of millions of tons. That small volume, coupled with high demand for tech devices, means tantalum is precious. Some estimates even suggest that if we do not find more sources or improve recycling, the available tantalum resources could be largely depleted within decades. It truly is a tantalizing situation. Much like Tantalus reaching for water, we have to be clever and persistent to keep getting this metal for our needs. Now that we know how to obtain tantalum, let's move on to the many ways how we actively use this metal. Why do companies go to such lengths to collect tantalum? What makes it so indispensable in certain applications? As it turns out, tantalum's curse, its resistance and ability, is also its greatest blessing in practical use. Tantalum might not be a household name, but it has quietly become a critical component in modern technology and industry. Its unique properties, especially its ability to resist corrosion and to form a protective oxide, are harnessed in variable fields. Let's explore the major applications of tantalum and why it's used in those ways. If you're watching this on a smartphone or a computer, there's a good chance that tantalum is at work inside your device. The number one use of tantalum today is in making electronic capacitors. Capacitor is a small component that stores electrical charge used in virtually every electronic circuit. Tantalum capacitors are prized because they can pack a lot of capacitance storage into a very small size, which is vital for today's miniaturized gadgets. Now, how does tantalum do this? Well, it's all about that oxide layer we discussed earlier. In a tantalum capacitor, a pellet of porous tantalum metal, imagine a little sponge-like nugget of tantalum, is used as one electrode. When this tantalum is exposed to air or an electrolyte, it instantly forms a tiny tantalum oxide film on its surface. That film acts as a dielectric, an insulating layer critical to a capacitor's function. Now, the combination of this very thin insulating layer and the high surface area due to the sponge-like form of the metal pellet means you get a high capacitance in a small volume. Tantalum's pentoxide is also an excellent dielectric. It can withstand electric fields while remaining insulating. Early work in the 1950s by Bell Labs, others, led to the development of these solid-state tantalum capacitors, and by the 1970s and 80s they were widely adopted in electronics. Now, your smartphone, for instance, might contain several, even dozens of tantalum capacitors, regulating power supply and filtering signals on circuit boards. They are common in laptops, tablets, automotive electronics, medical devices like hearing aids or pacemakers, and aerospace electronics, basically anywhere where reliable, compact capacitors are needed. Now, here is an illustrative fact. Tantalum capacitors became so important that during certain tech booms, like around the year 2000's .com and mobile phone boom, the demand surged and cost price spikes for tantalum. That's how tied this metal is to the fortune of the electronics industry. Now, aside from capacitors, tantalum also sees other electronic uses. It's used in some resistors and coils, and tantalum metal is also used as a material for electronic component leads, wires, because it doesn't corrode. Tantalum oxide is used in some semiconductor manufacturing processes too. For example, tantalum and tantalum nitride thin films are excellent diffusion barriers in copper-based integrated circuits. They keep copper from diffusing into other parts of the silicon chip. Tantalum oxide has been explored as a high permittivity, a high K material for things like dynamic random access memory, DRAM, capacitors, and and other microelectronic devices. Even in vacuum tubes, back in the day of vacuum electronics, tantalum was sometimes used as an electrode material or a getter. A getter is a piece of metal that soaks up residual gases inside a vacuum tube to keep the vacuum clean. Tantalum, when heated, can trap gases like oxygen or nitrogen thanks to its affinity for certain elements at a high temperature. Tantalum's heat resistance and strength make it valuable in aerospace and other high-temperature applications. While not as common as in electronics, you will find tantalum or tantalum-containing alloys in some jet engine turbine blades, rocket nozzles, or other parts that face blistering temperature. For instance, tantalum is added in small amounts in certain superalloys, mainly nickel-based alloys, that are used in turbine engines for aircraft and power generation. Even a few % of tantalum can significantly improve an alloy's high-temperature strength and corrosion resistance. The metal stability at red-hot temperatures helps components last longer under stress. In the nuclear industry, tantalum has been used in reactor components or experimental fusion reactors because it can handle intense heat and radiation without corroding quickly. In chemical processing plants, tantalum's acid-resistant nature is a godsend. It's used to make heat exchanger tubes, reactor vessels, valves, and pipes for handling hot, high-corrosive liquids. For example, a concentrated acid that would eat through stainless steel like it's candy might do nothing to tantalum lining. Using tantalum equipment can be expensive, but in certain cases it's actually cost-effective long-term because of the equipment longevity. Think of a pharmaceutical or a chemical plant dealing with strong acids. A tantalum-lined vessel could operate for years without maintenance, whereas other materials would require frequent replacement. Another specialized use in making laboratory equipment that needs to withstand acid, tantalum spatulas, crucibles, and hardware are used when chemists need to handle hydrofluoric acid or other reagents that would destroy glass or ceramics. Tantalum is one of the few materials that can contain hydrofluoric acid. Another area where tantalum shines, quite literally, is in medicine, because tantalum does not react with body fluids and does not cause allergic or immune reactions. It's considered bioinert. Surgeons and medical device makers have capitalized on that. Tantalum has been used in orthopedic implants and bone repair. Sometimes pure tantalum metal, porous tantalum, or tantalum-coated materials are implanted to replace or reinforce bone. For example, there are tantalum cranial plates to repair skull defects and tantalum markers that surgeons use in bones. Porous tantalum with a sponge structure can even serve as a scaffold that bone can grow into, providing a strong attachment. Some surgical tools and components are made of tantalum or have tantalum markers. If you've heard of surgical clips or staples, tantalum clips have been used in surgery because they are visible on X-rays. Tantalum is radio-opaque and won't corrode inside the body. They can remain in place indefinitely without causing issues. On occasion, tantalum has been used in dental work, though other materials like titanium are more common there. In the early development of prosthetics and even some early cochlear implants, tantalum parts were tried for their inertness. Now here we have one fascinating use mentioned in medical literature. Fine tantalum wires have been used to help reconnect severe nerves. The idea is the wire provides a path or guide for nerve fibers to grow along. Because the body doesn't reject the tantalum, it can remain in place as the nerve regrows. When you think of medical implants, titanium often comes to mind, and indeed titanium is widely used for biocompatibility. Tantalum serves as a sort of specialty option. It's even more inert in some ways. Titanium can form some oxide that, while generally biocompatible, doesn't match tantalum's record of basically zero reaction. However, tantalum is heavier and costlier, so it's used when its specific properties are needed. Now, if you enjoy photography or you have a high-quality camera in your phone, tantalum might be helping you take better pictures. Tantalum pentoxide is used in the production of special glass with a high refractive index. Basically, adding tantalum oxide to glass can make the glass bend light more effectively. This is very useful for making camera lenses and optical lenses that need to be powerful yet compact. High refractive index glass allows lens designers to create thinner or smaller lenses with the same focusing power. Historically, tantalum chloride was used as an additive in light bulb gases to prolong a filament life. This is quite a niche and mostly an old technology trick. Now, even in cutting-edge field, tantalum has made an appearance. Some superconducting quantum bits, qubits, in research use tantalum metal for the resonator or capacitor components. Tantalum's oxide is such a good insulator that it can help create stable qubits with long coherence times, as some studies have found. Now, this is very specialized, but it shows that tantalum remains relevant in the latest technology. So, why is tantalum called the cursed metal? Well, as we learned, the name comes from the myth of Tantalus, cursed to eternal frustration, reflecting how tantalum's discoverer struggled to make the element react. In those early days, tantalum was indeed tantalizing difficult to isolate, almost as if cursed by its mythological namesake. However, far from being a bad omen, that resistant nature turned out to be tantalum's greatest strength. Its unwillingness to corrode or melt easily is exactly why this metal became so important. In the end, tantalum is a metal of paradoxes, little known but ubiquitous in technology. Extremely tough, yet enabling the most delicate electronics. Born from a curse, but providing a blessing to human progress. But tantalum's legacy isn't only scientific, it's also deeply human. During the Second Congo War, profits from tantalum-rich coltan helped fund armed groups and fuel one of the deadliest modern conflicts. Even in our smartphones, this metal carries a reminder: technology can connect the world, but it can also come at a hidden cost. Next time you use your phone or enjoy the clarity of the camera lens, spare a thought for tantalum, the once cursed element that continues to tantalize us with its capabilities, ensuring that modern life remains as magical as any myth. Now, we would like to thank the members that support our channel. Thanks for doing that, we really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know more about another element that is tied to tantalum, make sure to watch this video on niobium next.